But I'll just give one more minute because I see a couple people now joining in. This is our first journal club, and the idea for the journal club is really to read some of the foundational papers of the cryo technique and also extend it. So that's why, for example, this offering has paired one of Jacques Dubochet's paper with the original vitrification paper with something new. And one point that would be very interesting, if this is a point of discussion after our journal club leaders present the papers, would be to see how far we've come or not so far we've come in the past decades. Okay, so today we'll hear from Dabu and Agata about these two papers on vitrification. So I'll turn it over to you.
So thank you very much, Dr. Edward. First of all, I would like to thank you to NYSBC and Dr. Edward and Dr. Mahira for providing this excellent opportunity to learn about the cryo-electron microscopy, which is very new field to me. And I'm learning this and I'm learning from the expert. This is a big thing for me. So in today's presentation, I will be presenting two papers. The title of the first paper is Cryo-Electron Microscopy of the Viruses. This paper was published in Nature in 1984. I would like to mention that the author of this paper were Marc Adrien and Jacques Dubochet. I would also like to mention that the Dubochet, he got Nobel Prize in 2017 for developing a cryo-electron microscopy for high-resolution structure determination of biomolecule in the solution. And the topic of the title of the second paper is a new method for vitrifying the samples for cryo-EM. And this paper was published in Journal of Structural Biology in 2016. So the point to be noted here is that the one paper was published in 1984, another was published in 2016. So we will see how the technology has advanced from here, from 1984 to the 2016, and what are the transition period, how the technology revolutionized in the field of structural biology, especially in the field of cryo-electron microscopy. So before going into detail, I would like to give a very brief introduction regarding the method of vitrification. So for cryo-EM structure determination, the protein sample must be suspended in a thin layer of vitrified buffer, preferably supported by a holy substrate. So here, this is showing a picture here, like this is the tweezer which is holding a carbon holy grade, and this is the magnified area of the grade where we put around 2 to 3 microliter of the samples is applied onto the grade, and about 99% of the sample is removed from using a filter paper. This process is called the blotting. After that, the grid is plunged into the liquid ethane. The liquid ethane temperature is close to like -80 there, and the grid get vitrified. So when the grid in this vitrified grade, we can see that these biological molecules are in a same layer, and they are well distributed. And there is a small thin vitreous layer around the samples that you can see these layers. If this layer are too thick, then we cannot image because the layer is too thick. And also if the layer is too thin, then also that will lead to the damage to the samples. Therefore, this vitreous layer should be of optimum thickness, which is usually considered as the little thicker than the largest diameter of the particle in the sample, and the particles should be evenly distributed. So this determines the vitrifications of the cryo-EM grid. So in this presentation, I will be describing these topic in each paper, where there's summary of finding in each paper, and what are the methodologies or instrumentation being used, and how the cryo-EM was used to solve the structures in those papers, and why I think this paper should be published or should not be published, what are the flaws or drawbacks in the paper, and why this paper good for the JC, or is there any other paper or alternative to these methods. So let's move to the first paper. The topic is cryo-electron microscopy of the viruses. So before go into the paper, I would like to mention the two things. First, like these are the previous two inventions that laid the foundation of this paper. The first invention was that the high resolution electron diffraction pattern can be obtained from frozen hydrated catalase crystals, suggesting that the feasibility of frozen specimen hydration technique. In this paper, the author have shown that this frozen hydrated catalase crystal can be diffracted after freezing at ultra low temperature. The structure of this hydrated catalase was solved at 3 angstrom. These clearly indicate that biological informations and the structure information can be preserved even at a very ultra low temperature after freezing these crystals. Another important discovery was that water molecule or any other aqueous solution can be rapidly cooled down without the formation of the crystal ice formation. So these two important discoveries, these led to the foundation of this paper. And let's go into the detail now. So in this paper, the author have developed a method to prepare and observe the frozen hydrated specimen from native biological suspension. So these are the 4 steps that were detailed in this paper, that were discovered or identified in this paper. First, the forming a thin layer of suspension, like applying a sample to the grid and then bloating it and then cooling it to the vitreous state. So, and then imaging of this cryo-EM grade into the microscope without rewarming above the devitrification temperature, which is around 140 Kelvin, and then observing it below the devitrification temperature and at a low electron dose to preserve the structure of the specimen. So I will describe each of these steps into the detail in my coming slide, but these are the summary, like how the sample was prepared and how this vitrification was performed and how the imaging was done in this. These are the summary of this paper. So in this paper, the author have used adenovirus type 2 vitrified samples. So they took around 5 microliter of the samples that contain around 5 into 10 to the power 11 particles per ml in hypotonic solution. These samples were applied into the cryo-electron microscopic grids. Here you can see, and most of this sample was absorbed using a filter paper, and then when this sample was still spreading over the grid, this grid was free fall into this liquid ethane from a height of around 6 centimeter into a 1.5 centimeter deep liquid ethane container. So here you can see the liquid nitrogen is present in the periphery, and the liquid ethane is present in the central container where the vitrification of the grid will take place. This is the magnified area of this vitrification grid, where we can see these are the carbon support, and in between them this is the vitreous sample, which contain amorphous water without any ice samples, and the samples are present in a monolayer which can be imaged and of the appropriate vitreous thickness. So this grid thereafter was subjected to the Philip 400 electron microscope, where it was kept below a temperature of 100 Kelvin. So Kelvin temperature, and the layer of this thickness was around 1.2 micron thickness, and the magnification was around 12,500x. So here we can see that in 1984, all the steps that were performed, like preparing a grid and then vitrification and then imaging, these steps is similar to the one we do today, but the how we do, that is the only thing that matters. Like we have the principle or the fundamental behind this preparation of the cryo grid is same as we do it today also. So using this method, the author have determined the structure, determine the imaging, the structure image of the adenovirus type 2. So the author applied this method for T4 bacteriophage or VSV virus or adenovirus type 2, and prove that this method can be used to image any biological samples. So here you can see that these are the well scattered and dispersed adenovirus 2 virus particles. Here you can also see, if you can see here, these spike proteins which is present on the surface of this virus, and you can also see here some thick region of the ice, which is difficult to image. So this clearly suggests that the method that was developed is feasible and can be applied to image the biological samples. Thereafter, the author also applied this method to take for the T4 bacteriophages. So here you can see these are the head regions of the bacteriophage, and these are the tail region, and you can even see the DNA in this image. And this is the like thick area where we cannot see anything, but in this area where we have the right thickness of the vitreous ice, we can see these virus particle over there. So author use this method for the imaging of the semi-liquid forest virus, vesicular stomatitis virus. And so this clearly suggests that at the time of 1984, this method was developed. So basically, why this paper is more important, this is I want to focus on this, like this method was developed first time and why it is important. So I think this is important because the previous invention, like the previous technology, which is a transmission electron microscopy or SEM, where the biological material is dehydrated and fixed using let's say a chemical like for paraformaldehyde or glutaraldehyde, which can fix the sample and dehydrate, remove the water molecules. But in case of this cryo-EM sample preparation, we are not removing any water molecules, because the water molecules is a very important component of the organism and the cells which maintain the internal structure of these organisms. Therefore, in the previous invention, the water molecule was dehydrated, like removed from the cells. Therefore, that's why we were not able to get a high resolution structure. But in the cryo-EM, the water molecule is retained in this biological sample that lead to the high resolution structure in case of the cryo-EM. So that's why I think that this paper has advanced the field of the cryo-EM as well as the structure biology. So so in this paper, because this method was developed very first time, so there are several flaws in the paper like that need to be improved, because everything was manual, it has to be done with the hands. So therefore, the preparation of this vitrified specimen of consistent and reliable quality still remain a challenge. I would suggest this preparing the vitrified grades, still we are not like 100% can get high quality grades in a one go. We have to repeat it like few times. So I would suggest even at the time, this consistency and the reliability still remain the challenge. And also in this method, the sample layer was of around 1.2 micrometer thickness that can be further improved in this paper. This was I would suggest another flaw in the paper, but some area were too thick that were difficult to image. This was another important point to be noted. And finding the holes covered by the ice of precise thickness was another problem observed that take around hours or a large amount of times to find the grid of right thickness. And also the author also observed here that when they were collecting the data, the water molecule was mobile under the electron beams. So these small molecule in the solution or even the biological structure could be rearranged. So this was another problem that was detected first time in this paper. And for some time, the upper and the lower side of the particle do not appear symmetrical. So it could be because these biological molecules, they were reacting or associated with having some interaction with the material of the grid. That could be the one reason for this. This is what the author have explained. So these are the some flaws in the paper, but still I would suggest this was a very good paper, like how this method was developed and what are the basic principles behind it. So again, I would like to focus each and every step here is remain the same that we do it today, but we do it using Vitrobot, or we have automated robotic machines that do all these steps, but the fundamental principle and the basic concept is remain the same in the method that was developed like 25 years before from now. This is my second paper, which I would like to present, a new method of vitrifying the sample for cryo-EM. So in this paper, The author have developed a very high calibrated automated device, which they named it as a spotitone for preparing the vitrified sample. So in this is totally an automated device, which is controlled by very high quality software and the hardware, and which were designed by the team of engineers, which is very difficult for me to understand, but I will try to understand each and everything that was mentioned in this paper. So using this device, the author have developed a robust and reliable method to prepare vitrified samples of suitable ice thickness. This device is coupled with a new self-blotting, because in the previous paper, we are using a filter papers to take out the extra material from the grids. But here they have a self-blotting grid that provide a method for spreading the sample to the thin film without the use of any externally applied filter paper. So these self-blotting grid were containing the nanowires. I will come to the detail about those nanowires. And in this method, the author have used the amount of the proteins or the biological specimen that is required is in a nanoliter quantity, not in a microgram. Like about 10 nanoliter of the protein sample or biological sample is required here for a one grid. So in 1 microgram, we can prepare at least 100 of the grids. So the resulting grids from this method, automated method, contain large area of the ice of well-defined thickness and evenly distributed single particles. So this is the main finding, that they have developed a automated device that can confirm this vitrification of the samples, as well as transferring a grid from liquid ethane to the grid box in liquid nitrogen. So this is the image of the Spotitone 1.0 device. Here you can see you have a 3-axis grid robot. This is a tweezer here, which can move the grid from in 3 directions: upward, downward, or horizontal direction. And this is a 3-axis dispenser robot, which contain these the piezo tips that can take the material and transfer it or spot it onto the grid. So I will show a video of this. Here you can have the samples station where the piezo tips comes and get the samples, and then samples are washed. These piezo tips are washed because we don't want the sample to get dried onto the tips that can block those tips. And then after washing, the sample will be dried over here. So before going to the detail of the method, I would like to show a very small video, which is about a 2-minute video. Here you can see, this is the station. These are the piezo tips here. This is the sample over here. The sample is being aspirated into the tips. After taking the samples, it will go to the washing station. So this will remove the extra samples from the tips, because these tips are very tiny tips. If even a small dot of the samples can block these tips, or sample will be dried. So this is why we wash these tips. And also here we are dealing with the protein samples in nanoliters, so we don't want to contaminate our sample with this wash solution or buffer. Therefore, the tips will be dried over here. So everything, all the process is automatic here. Like it is controlled by a highly designed software and this hardware. Now you can see this is moving in horizontal direction. Now, so this is the drop of this. I will explain what is that. Now it will become in a horizontal, this is a vertical direction. Now it will go into the horizontal direction to load the samples. So this is the horizontal direction. It will go close to the grid. So this grid is here. And these piezo tips, they will very accurately load the tip, and it can be queued, like several samples can be queued in a one go. So this is how this spotty tone works. So this is a completely automated device, and it is controlled by a well-designed software and the hardware. So the same thing here, that this is just picture showing that we have the samples over here. This is the wash station, and this is the dry to make the samples, those tips dry, and then it will deposit or dispense the sample over the grid, which is grid is also like can be moved in 3 directions. And then this piezo tips station can be moved in 3 directions. And once the sample is like deposited, then it will be vitrified into the liquid ethane. And then from there, the grid will be automatically transferred to the grid box in liquid nitrogen. So I will come to this method. So these are the outline of this method that we just saw here. Like a small volume, about 1 microliter of the sample is aspirated into the piezo tips, and then the tip is washed with the water to remove excess of the samples from the outer surface. Because this is important, because we don't want any samples in the tip, over the tip, that could leak, that could clog the tip. And then the tip, after washing, it has to be wiped to make the tip dried, and which could which could interfere with the spot formations and the precise targeting. So here the two things which is very important here. One is this piezo head is positioned in front of camera, and the spot formation is checked for the size and accuracy. So this whole process is controlled by the software. There will be a video camera, and then these images will be reflected on the computer screen, where we can position where we want to put our spots. This piezo head is positioned in front of the grid at a distance of around 1 mm and record the drop locations on the grid relative to the tip. So this software is in this automated process, the software can be queue up a series of targets for spotting with a specified number of the drops, and the spots are dispersed based on the queued order. Like you can give a number to them, and then they will be deposited in that order. And then the grid is plunged automatically using a tweezers into a liquid ethane, and then after that the grid is transferred to the liquid, from liquid ethane into to the grid box. So all the process from starting from the taking the samples and transferring the grid to the liquid to the grid box in liquid nitrogen, all are automatic, highly controlled. They have like this software, this device, this Spotitone has a highly controlled motion, tweezers and those other things that control precisely. And that's how this method involve minimum human interference. Everything is controlled by the computer and the software. But the method that was developed in 1984 is the process, like there we are doing with the hand, here we can do everything with the robotic system. So I would like to give very brief introductions about what is the Spotitone hardware design. So this is a very easy to use and has a robust robot motion controls, and it has a more reproducibility and the piezo dispensing. So all the steps that are required for the vitrification of the grid are now automatic, like it can be controlled through the software. And these steps include the washing and drying of these piezo dispensing tips, checking the samples spotting on the grid, and aligning the grid and the tip location to ensure accurate targeting, queuing up multiple spots, plunging and transferring the grid from ethane to the grid box. These steps all are automated, which is possible through this Spotitone 1.0 hardware designs. And this is very important when it comes to the reproducibility of the system of the experiment. So that's I think this is a very good design software and the device used for the vitrification. Now let's go to the software design, software integration. This Spotitone 1.0 software integration. So this software, like it comes in a single software package that can control various things like output control and output, such as motion controller, proximity sensors, actuators, video cameras, all are combined into a single software. And the time here can be reduced by a lot because this software has click to move and click to spot functional in the software. Like you can just decide your coordinates or the position of the position of the spot, which can then be controlled by the software. We just have to, because we will have a video camera of the grid, like the video picture of the grid, where we can decide where we want to put the samples, and also we can have multiple samples queued by one after other. So each individual piezo dispensing tip is automatically calibrated to determine the relationship between its position on the video feed and the physical coordinates of the robots. And the image recognition software is used to recognize the position of the dispenser and match it with the XY coordinate of the video feed. And after calibration, the user is able to click anywhere on the video, on the live video, and tip to move to a new position. So this, and also user has the option to queue up several targets on the grid for spotting the same sample at the different locations. So these are our function which is controlled through this software that can control this complete device. So in this device Polytron 1.0, we have like different motions, like how the tweezers move, how the tips are moving and depositing the samples exactly at the right location in the grid. So these are possible because of the improved motion robotics, which have been integrated with this machine. So here, what the author have done with the added freedom of XY movement of these tweezers, the people can, or users is able to replace place the grids anywhere in the front of camera without concern of plunging accuracy. And also during the normal operation of the robot, the piezo dispenser are either in vertical orientation to take the samples from the sample station, and then depositing, and then this dispenser will be in horizontal direction for dispensing the samples over the grid. So here, another important thing, like here, the grid after dispensing the sample, and then the grid will be vitrified automatically in the liquid ethane, and then the grid will be transferred from liquid ethane into the grid box. So this is possible because of this is in this Polytron 1.0, the tweezer are mounted in independent 3-axis motion system, where we have X, Y, and Z section. So we have 3-direction movement, free movement here. This freedom of movement allow free positioning of the tweezers and the grid in the front of camera and the piezo dispensers. The additional X and Y axis of the motion allow the movement of the grid from the liquid ethane dewar to a designated grid box in the liquid nitrogen. The time to complete this transfer from the ethane to the liquid nitrogen is as similar as the one we do manually, like with our hands. So like it take about 2 seconds or 1 second. So now let's come to the self-blotting temp grids. In this method, the author have used this self-blotting grid, which we called, this is like a normal grid. And in this normal grid, we will have several wires that called the nano wires, which is formed of the cuprous hydroxide, which is which are of consistent length as well as diameter on the copper surface. So how these are generated, if we have a one grade which is copper palladium grade of 155 mass grade from this company, then first these grids will be cleaned by sonicating in acetone for 1 minute, followed by 1 minute sonication in ethanol, and then wash into the water and dry it in the air. After that, the green will be put upside down, the copper surface down, on a 20 microliter drop of 1.13 molar ammonium persulfate and 2.5 molar sodium hydroxide solution for 3 to 6 minutes. During this 3 to 6 minutes, there will be some chemical reaction will happen that will generate these nano wires on the copper side of the grid. And then this grid will be transferred to a float or to sequential drop. This will be washed to stop the copper, these nanowire reactions. And then this formation of these nanotubes or nanowire was checked under the light microscope. And these are the images of these nanowires. Like this is the like nanowire image where the chemical reaction was proceed for 4 minutes. Here 6 minutes, and here the 10 minutes. So you can see there, like here about 20% of the nanowire tubes have formed here, like close to 70 or 60%, here like 100%. In 10 minutes, 100% of the grid is covered with these nanowires. So these nanowires, the advantage of these nanowires is that when the sample is applied onto the grid, the excess of the sample will be wicked by these nanowires and leaving behind a very thin layer of the sample over the grid. So this exclude the use of the filter paper, like we absorb excess of the sample using a filter paper, but here this function is achieved by these nanowires. So using this method, the authors of this paper have tried to image the ribosome, like different biological samples, to prove that this method can be easily used for the vitrification of different biological samples, and that give a very high quality images. So here this is the grid, this one of the spot on the grid where the samples were deposited by the spotted hone. These yellow rectangular square you can see here. So this is the magnified image of these squares here. You can see the samples were well dispersed, and also they were like in a similar thickness. There's no like big variation in the samples, and then the samples were imaged at a very high magnification. You can see this red square here. This was magnified, and you can see this single particle, even distribution of these single particles, and that shows that the process was carried out like in a very controlled manner, and the samples were of the very high quality. Similarly, author also used the same method for the other biological samples, which is hemagglutinin HA, where vitrified onto nanowire grid. Here you can see that the samples was when applied to the grid. You can see the image, the low magnification image. The sample were homogeneous, vitreous, and into the same layer. And these are the high resolution image. Here you can see the single particle distribution of these particles. So this clearly indicate or suggest that the method was of the reproducible quality, and it was totally automated and was controlled precisely by the automated device. So advantage of the current paper, this is a completely automatic and precise method which is controlled by newly designed hardware and software. Minimum human interference was involved in this method. Therefore, because it is controlled through the robotic system, so it has a very high reproducibility. And it can be applied all the biological samples. In this, one of the major advantages is that in the single square of the nanowire grid contains several thousands holes covered with the vitreous ice of appropriate thickness in the particle distribution. So all the data can be acquired by imaging the single square of the grid that omit the need for searching the different area of the grid. This is important because in the conventional method, we have to find the area of right thickness. If the area is too thick, we cannot image them. So here, if we are able to see the single square, we can get the complete data set from the single square, which can preserve or save a lot of time for the imaging. So what are there? Because in this paper also there was some flaw that I would like to mention, how we can improve them in the future. So the nanowire we are using over the grid, sometimes they vary from one batch to another batch because of the impurities in the copper. So this is the one of the flaw that author mentioned, that this could be one of the major drawback in the paper. And another one is that the current version of the spotted hone, it take about 1 second time to withdraw the tip and then deliver the grid to the liquid ethanes. So this is like 1 second, which author think it is during this 1 second, the sample can evaporate or dry because the sample is present in a very thin film over the grid. So this time they're suggesting that it can be reduced to the 10 millisecond order to reduce this evaporation or drying of the grid. So this was another flaw in the paper. And another thing here is that because in the spotted hone version, about 1 microliter of the sample is required, but essentially we only need 10 nanoliter of the sample for one grade. So therefore, in 1 microliter of the sample, hundreds of the grade can be easily coated or prepared. So this is the author think that this is the waste of the sample that are precious and difficult to make. So they want in the future to increase this ability of the spotted tone, where they can just reduce the volume to the 100 nanoliters or lesser than that. So this is a good choice for the journal club? I would suggest yes, this is a good choice for the journal club, because of this revolutionized technology, now we are able to prepare this vitrified grade in an automated machine, which is a highly reproducible, and also it is highly symmetrical, which we can easily perform without the minimum interference. So I would suggest, but the principle that was developed before, 25 years before, and now it remains the same, but the technology has been advanced and it has revolutionized the field of structural biology. This is what I would suggest. And also another questions was asked that if there were any other set of the papers. Yes, there was a paper that was published before this Potitone version 0.75. In this paper, the author was using 2 cameras, one for the grid and one for the piezo tips. So, but in this current version of the paper, where they spotted on 1.0, one camera can be controlled everything here. So this is the advancement of the previous paper for this for the vitrification system for cryo electron microscopy. So this was the paper for these 2 papers for today's presentation. I am now open to any questions.
So I have a question. So then what would you prefer to use if you had the choice?
If I have choice, because to save my time, let's say if my sample is very precious and I have very less time, or I have multiple samples that I want to process, then I will definitely go for the automated device.
I wonder if I can put Mahara on the spot, that because she has used all our plunge freezers as well as a Chameleon.
Mm-hmm.
What does Mahara prefer?
Which I prefer to use in terms of the results it gives me, or just ease of use?
Well, answer both. That'll be interesting.
Okay, so I first started on the Leica. So I thought that was it. It was pretty good. It's pretty easy, because I then used the Vitrobot. And the thing about the Vitrobot is this little mobile station, if you've ever used it. So people do this differently. So when they teach you differently. So when I was taught to like hold the tweezers and then move the station out of the main unit, and then put the grid in the grid box. And every time I did that, I would always like crush the grid. So I was like, yeah, this Vitrobot is no good. So then eventually I had to practice on the Vitrobot, and I stopped moving that little movable station, and I just put the grid right there. And honestly, the Vitrobot's pretty good. So I say if you don't know anything about your protein, the Vitrobot's pretty decent start actually. The Leica is also pretty good. I think in terms of the consistency and the grids you make for either of those machines, they're pretty close, but obviously never exact. So if it works once, it may work again, but you have to keep everything the same, like when you put in your filter paper and stuff like this. So I try to keep it in a certain order so I always can know what to expect. The Chameleons, this one, I think it's pretty easy to use. You don't have to directly handle grids, so they're not going to be crushed, which is really great. The only thing is like getting used to seeing the video in which it gives you. So the video shows the wicking process, right? And you as a operator have to determine how good this grid will be based on this image. So sometimes that takes getting used to, because sometimes images may look empty to you because they're wicked a pretty decent amount, but you can't tell whether there's ice in there or not. So that comes with experience and using the machine often. So yes, so I think all of them are pretty good to use. Maybe the Vitrobot is actually the hardest. Only because of the number of settings you can control. Also.
They're in the automated device? The Vitrobot.
Say it again. Oh no, yeah, the Vitrobot is probably, in my opinion, the hardest. But then, because you have more available to you to change, it's better to have less to change, so you have less to worry about. But the Chameleon's pretty easy to use. I would say that one's second easiest, only in terms of handling. So you don't really have to handle much, and that's pretty good. I think for a first-time user, you just click, and that's it.
Oh, yeah.
So Mahara, if 10 people walk in the door, what would each of them use? What is used the most here at the center?
I would say top is Vitrobot, hands down, and then the Leica, and then the Chameleon.
So why I bring that up, I think vitrification is an issue and a bottleneck in cryo-EM, primarily because we don't have a streamlined process to know that if you have a sample that you'll consistently always be able to create grids that you can assay the sample versus the process of sample preparation. And the other thing that comes into play is that there's more pressure in sample preparation because the workflow of cryo-EM, the time that it takes, is quite resource intensive. We collect data sets in a matter of hours, maybe days, depending on what your target is. And if you have a bad grid or a good grid, the workflow takes a similar amount of time. You can triage a bad grid faster, but let's say it's not black or white. Let's say it's just a so-so grid. Is that a useful grid or not? And then you're now fighting with the sample preparation and not actually assaying your sample. And furthermore, that impacts because you can't quite readily screen 96 grids. And so if you have 96 conditions that you want to screen, but each condition may also be compounded by that if you made 4 grids, they might not be identical. Oh, let me take a step back. Mahara, if you made 4 grids, how identical are they?
Which machine do I make them on? Yeah, if I make them on the Vitrobot or Leica, I want to say they're pretty close, maybe like either from 40 to 60% alike.
So then, so you have to do multiples or duplicates, or depending on how you arrange your experiment. 1 grid would not be enough. And so that's why there's so much pressure in vitrification and sample prep, because if you can automate that or streamline it in some way, then you can go after more targets. Also, as you said, sample limiting. If you have limited amount of sample, you might not be able to make 4 grids or etc. Why do we say 4? That seems to be a nice round number. And if you look at standard crowd grid boxes, there's enough to do 4 grids per box. And the time it takes to make 4 grids is about reasonable. So I don't know if 4 is really a magic number, but typically it's very straightforward in the workflow as of today. That might change and best practices may change. Any questions from the students? Is vitrification a problem for any of you? How many people have tried plunge freezing and encountered issues? And this is a good forum to bring it up.
So I have a question. This is Agata. I was supposed to help answering, but I have a question. So regarding the older paper, they in their conclusion they said that as Dabu mentioned, that they saw undoubtedly that the water molecules were mobile and that this resulted in molecular bubbling. What does it mean and how was this manifested in the imaging? Can someone enlighten me?
I think I will try to give an answer. Maybe Mahira and Edward can give a very solid answer for this. So I think this depends upon the vitrification state of the samples. If the samples are like perfectly vitrified, they won't, the water molecule may not move under the electron beam. But let's say if the samples are not perfectly vitrified, then the biological, there will be some water molecules there and some interaction among the biological molecules that can give some problems. So I ask Dr. Edward, could you please have any answer for these questions?
Well, I guess I'll extend the discussion a little bit more. There has been a lot of effort to look at what happens when you cool samples. And if you cool too slowly, then you may actually add quite a bit of stresses because hydrogen bonding of water, and you can have many different forms of water. And there has been thought that maybe you don't want to cool so rapidly, or you want to try different temperatures. You might want to have different resting points, because when you freeze something, you sort of, it's frozen hydrated, but it is in sort of a fixed nature. Once an electron beam hits your sample, that could put enough energy in the system to allow movement of the sample, because just because it's frozen doesn't mean it's static. There's still motion. Molecules can still move in the vitrified state. And also, certain stresses may cause beam-induced motion. And so there's been more recent papers looking at different vitrification methods, different rates, and how that may be better or worse.
Maybe it is due to like when electron beam fell on hit the biological sample, there could be some energy that is transferred from electron beam into the biological sample that raise the heat or energy that make the vitreous state a little bit in compromised position.
I wonder if we can find a couple more papers and forward that to you, so that's a good topic of discussion, in the sense that things are not as static as you believe, and particles do move when we are imaging, because the electron beam has quite a bit of energy. And also, if you keep on imaging, you will destroy your sample, if not denature it.
So are there like special parameters that you look at that would tell you exactly that something happened with the image and that the particle actually have moved? Or because I referred this to crystallography, and perhaps this is too far-fetched comparison. I mean, with 2 angstrom resolution, the rule of the thumb is that you have 1 water molecule per 1 residue usually, but in this paper from 1984, I doubt they went to 2 angstrom resolution. That it was probably much lower. So I'm just trying to envision how one can tell that there is a movement in the water, and that it causes the molecular bubbling, whatever it means. So I was just curious about this technical terms that I'm not really familiar with. Yeah.
I don't know if you can really track water, because
precisely
the vitrified buffer for us is noise.
Yeah. Okay.
It's a lot easier to track the molecule of interest, especially when you go into image processing. And if you have a map, then you could sort of see if there are other effects. We don't have very good ways of analyzing, let's say, voltage differentials or lateral stress, and how that might affect the molecules, and tease that out from poor biochemistry or damage or other effects from imaging as well. So there tends to be a lot of factors that are sort of rolled into some envelope function that we hand wave. So that is hard, and that also impacts sample preparation in general.
Okay, thank you.
So this is still an emerging field. I think there's certain best practices that has helped minimize, but I don't, again, if you said you had the same sample and the same protocol and you gave it around the world, it might not be so straightforward to reproduce. Hopefully we're getting better at that, but there is some variation. And until we get better at that and minimize the variation such that you give the same sample, have the same instrument, doesn't matter if you're 5,000 feet in the air below sea level in one locale or another, you would have consistent reproducible results. Until that happens, I think there'll still be some variability and more art in the science. On the other hand, I don't know how much minimization is required. I don't know how variable we can be and still achieve the same result. And that is something that'll be interesting as we collect more data.
Thank you.
So there's a question in the chat. So I don't know if Mahira wants to field that. If other people have more practice, then they could also field that. But it's more on the question of there's a lot of different parameters that we can change, specifically the weight parameter. But I don't know, Mahira, how many parameters do you actually change when you plunge freeze?
On the Vitrobot, I just change the blot time. So I don't change the force at all. I always use 0. That's the only thing I change. And on the Leica, I just change blot time as well. And on the Chameleon, I just change plunging speed.
I think anything else that people change would be sample specific. Like, for example, if you want to plunge slower or you want to wait before plunging, rather. The Chameleon is complete opposite because you don't want to wait. How fast do you normally run the Chameleon?
So honestly, from the actual grid making process will take you less than an hour. So I want to say like maybe 20 minutes for 4 grids if you're really deciding. But just from like start to finish for 4 grids only, it probably takes an hour or so to set up the machine.
On any machine.
Oh yeah, this is true. Well, actually the Vitrobot may be faster. And the Leica as well. It depends the humidity you want.
What is the time from application of the sample till vitrification in liquid ethane? I think that is just an open question. And so some people want to wait, some people don't want to wait, and that is very sample dependent. So there's no hard, fast rule of thumb. Right now, whatever works. And I think that's the complicating factor. Just because it works doesn't mean it's robust and other people can do it. So there's quite a few people who can manually plunge freeze. For example, literally just have a gravity plunge freezer or with their hand plunge, and they with their hand blot and then plunge rather. That requires a lot of experience. So that can be done, that can be trained, that can be learned, but it may not be so scalable. Waiting, so the reason we have something known as the air-water interface, so there can be an interaction with the air-water interface that can be favorable or unfavorable. Unfavorable in the sense that it could lead to denaturation. Favorable in the sense that if you have a support film, you could concentrate your sample. And if you look at the concentrations you use for negative stain versus cryo versus blot-free vitrification, they tend to be quite different. Other questions, other comments?
Yes, this is Agata again. So I have another question. So what would be the best neutral buffer for the imaging that would not negatively affect imaging, such as it wouldn't decrease the contrast or, I don't know, would not make the ice super thick. I know that the buffer is sample dependent, meaning I should keep my protein in something it makes it happy. But I think, for example, or I've read that if one keeps the salt above 0.2 molar, then it may decrease the contrast. So what are your thoughts about what should be like the maybe most neutral buffer I should keep my sample in?
I think that's a complicated question because the best buffer for imaging is water, because the electron contrast between your sample and the support film would be negligible.
Okay.
But that doesn't help if you can image your protein that's denatured.
Correct.
So then you would have, that's why people will add glycerol. They will add a couple molar salt. They will add detergent. It is a compromise because they would rather image a near native complex. And that compromise is outweighing the best imaging quality.
Okay.
So if you can get away with everything, that's why it's sample dependent. If you have to make a compromise, then it really depends what your biological question is. For example, is an artificial high resolution structure useful to make testable models? So you could have a condition where you get a 1.3 angstrom cryo reconstruction, but is biologically meaningless. But perhaps the high resolution could not make it not so biologically meaningless because it will allow you to do testable models and will allow you to create a really nice PDB.
Right.
People usually try to go after transition states. That's hard, especially if they're rare events and if they're not stable. The disadvantage for single particle techniques is that there's not a way to lock in a particular conformation, or crystallization is a purification technique as well. So it makes it a little bit harder to just, have a situation where you overemphasize a particular state.
Yeah, thank you.
It's not impossible. It's just that, again, it's a compromise by sample and what your target is. There are rational ways to do screening. They do now sell screening kits to try to look at optimization of buffer. So we sort of touched upon that earlier, but there are rational designs of are surfactants useful or different salts useful. So very similar to what they've done in crystallography, and that is based upon a lot of published papers. Now the question would be, you would need an orthogonal technique. So just because it's EM compatible, you need an orthogonal technique to make sure that it is biologically relevant in this context.
Spotted on would be good for that, right? One could test different buffers, sample in different buffers on one grid, essentially.
You could do a gradient, potentially, because Spot On has a couple heads that can do two different liquids. Otherwise, yes, you would have to do several grids. It wouldn't be on one grid. The question would be, what parameters would be useful to vary if you had two different liquids? And if also the time scale is amenable, then you could do, but Spotted On is not set up to do different buffers on the same grid. So you wouldn't be able to, say, screen 96 different buffers with one sample. You would be able to have just two nozzles with different liquids.
Okay.
So that is that's why the field is still emerging, because the goal would be to have multiple separate samples on one grid, because that would cut down a lot of the overhead for the cryo workflow.
Thank you.
If you have a controlled room, then it doesn't matter if you are in the summertime in the desert, in Florida, where it's always humid. And if you have an environmental controlled room, so the temperature is stable, the humidity is stable, so then all things being equal, it will be equal all year round. If you have samples that change depending on the year, then it would change depending on the year. So you have to tease out the sample preparation, environment versus the sample. There were some initial work done on memory proteins using frog oocytes, and the maturation of the oocytes differed depending on time of year. And so they would harvest oocytes and inject it with RNA and try to overexpress some proteins. And depending on the time of year, the expression level and stability of the overexpressed protein changed. So there are differences in time of year that are not necessarily solely due to humidity or due to it being winter or summer. If you're in an HVAC temperature controlled room, then it's pretty consistent. So that's a real asterisk, because though you assume, do you know? So our dehumidified rooms are monitored, and we have monitoring, and so we know that we're always below 10% humidity, and we always know that the temperature is stable. It might be one of our DH rooms is a little bit warm, but whatever the temperature is, it's stable. And then when you're transiting in and out, you're going through a controlled lab environment, and that should have no effect. If you're plunge freezing in a lab that is not humidity controlled, then you could have very dry winters and very humid summers. And in that case, that is something you want to control. Also, you want to control if, let's say, your workflow for sample preparation means I'm going to work in a dehumidified room, but I'm going to prepare grids in a different lab that is humid or dry, and doesn't use compressed gases unless they just use oxygen and nitrogen that is in the air. And you might have different contaminants depending on year. And if you could have a lot of pollen in the air, even though in your lab. And so then that's separate. So that's what I mean. You have to make sure, are you in a controlled environment in all steps of the way? If so, then you would have minimal impact. The reason why I'm on this line is there's a question in chat saying grids frozen in the summer versus grids frozen in the winter. The same Vitribot parameters gives different ice thickness. Apart from Vitribot humidity, the room temperature and humidity also matter. So there are a lot of things that can impact. And if you really are going to be reproducible, you want to separate the parameters and try to be as consistent as possible. Something else to think about when you're varying parameters. If you're varying parameters by units you cannot reproducibly reproduce, that is an issue. For example, if 1.25 versus 1.5 second blot times is a difference between completely dry and too thick, you have a problem, because technically that deviation is very little, and it should not be as reproducible as you think, versus if a blot of 1 second versus 10 seconds would be the difference of very thick and completely dry, then you have at least more range to play with. So if that's beyond your control, then it's going to be a very challenging problem. So again, this is sample dependent. So you might not want that to be your range. That just so happens to be your range. Then that's when you probably would look at different vitrification techniques, because it's untenable to have a difference of 0.25 seconds being dry or completely opaque. That has happened to some of our users, and it's just very complicated to solve because it's sample dependent. So again, what comes up? Sample dependence. That's sort of the reality of sample preparation, and vitrification needs to be as consistent. Otherwise, you're fighting with too many variables. Okay, Dabu, any last comments? Agata, any last comments?
Well, I'm looking forward to the further development of Spotaton. I really like it. I feel like it's a huge step forward in terms of automation and precision and the amount of or the volume of the sample that's being used. Yeah, so I really like it.
There is another device. It's called Cryo Writer, the Vitrojet. And so that is another blot-free vitrification that uses little sample. And
You guys made it?
no, that's from Peter Peters. So there are two main blot-free vitrification devices, and they use cryojets. And so the advantage of that is that you potentially could have samples with a lot more mass, meaning clipped grids, or potentially cells, tissues that you want to vitrify, not just single ones. So that if you are interested in looking for blot-free vitrification, don't look just at Spotaton, look at the Vitrojet.
Okay.
It's just showing you the direction the field is trying to move to automate sample preparation as well as find alternative methods, because as you look at the 80s papers to now, we still use blotting and plunging in some way. And that's the bulk of how most of the samples are prepared, especially for a single particle. And that could mean that it's tested, tried and true, but there are some complications with that we identified. If you're lucky enough to not have any of those complications, then simple might be better. Dabu, any last words?
Thank you all. I think we are good. I like the Vitrobot, like the Mahira said. The Vitrobot is the good method. Here we have some control also over there, like manual control we can do.
Okay, well then, in that case, we'll wrap up. Monday, we'll shift to a different section of the course. We'll begin the, what do you call it? Electron crystallography sections. We'll start off with micro ED on Monday with Bill Rice, and then the week after, we'll talk about helical, or I guess that follows on with 2D crystallography. So there are three main modalities of EM, and that's single particle, micro ED, or I'll roll in micro ED and 2D crystallography into one batch, and then there's tomography. All that can be done. All three modalities of EM can be done on the same microscope. Okay, so see you soon.
See you. Thank you. Bye-bye.